So let's start with a short presentation. And some general consideration, let's say. Generally speaking, an embankment is an area of material used to support a roadway or a train track, or also to hold back water. It's generally made of compacted soil, and as you can see on the pictures that I put on the slide, they are widely used, going from a road embankment or whatsoever to embankment dam. As I just mentioned, these embankments are generally made of compacted soil. Soil is a porous material and have different design properties under drain and undrained conditions. Drain condition means that pore water can easily drain out from the soil matrix, when in the case of undrained conditions, the pore water is unable to drain out, or the rate of loading is much quicker than the rate at which the pore water is able to drain out. The existence of drain or undrained conditions in soil depend on the soil types. Is it a sand, gravel, clay, silt? It depends as well on the geological formation, such as fissures, embedded sand layer, etc. It depends as well on the rate of loading. Experiments have shown that grain condition almost always exists for coarse grain materials such as gravel and sands under static loading. This is due to the large permeability of this material, so the pore water can quickly drain out. On the other hand, due to low material permeability, undrained condition almost always exists for clays and silts when subjected to quick static load. Let's talk about the drainage condition in Diana. It can be specified at the material level when you add the drainage aspect. As you can see on my screen, these are the options that you need to include at the material level, and as you can see, you can choose for drain behavior or undrained behavior. The undrained behavior can be modeled by defining an excess pore fluid pressure in the material. This is undrained behavior with penalty factor. It results that the undrained compression modulus Kf is equal to the drain compression modulus K times a penalty factor, the one that you will enter. Alternatively, the Kf can be computed from the Skempton's B parameter and the drain compression modulus K. This is what we call the undrained behavior with Skempton B parameter. And finally, you can also model the undrained behavior by specifying the undrained compression modulus Kf. This is the undrained behavior with the fluid bulk modulus. And this is the one we will use in today's live demo. Let's now discuss the analysis type that we are going to use today. So today we will use the geomechanical stage construction analysis. This application was introduced in Diana 10.3, so our current commercial version, and has been designed for the purpose of making it easy to define the typical geotechnical analysis in practical engineering. For the people who are familiar with Diana for a longer period, we can say that it's a kind of simplified version of the phased analysis. Such analysis can be characterized as a combination of soil, water, and structures, where for each of these components, nonlinear material behavior may be assumed, and where the history of the different construction stage are considered. Considering the water pressure, there are 4 types of stages that can be defined, whether no water present, which will be the case in today's demo, water level specified for steady state, water level computed for steady state, and water level computed for transient. So for specified water level stage, user must define the respective water level in the model. For a steady state computed water level, the user must define a boundary case that defines the water level. And for the transient computed water level, the user must define a boundary case for the initial groundwater condition and may define additional boundary condition to which time function are assigned. When a stage with computer water level, steady state or transient is chosen, Diana automatically perform a groundwater flow analysis and subsequently a structural analysis. But for more detailed information, I invite you to refer to our online documentation. Regarding the changes allowed when using the geomechanical stage construction, you can activate or deactivate part of your model, such as mesh sets, piles or pile sets, reinforcement or reinforcement sets. You can also activate or deactivate loads or boundary condition for the groundwater flow. You can activate or deactivate support or fixed head. And finally, you can also change material of active part of your model. And this is something I will show you in the live demo today. It's good to mention that this geomechanical stage construction use automatic deactivation of interfaces or boundary condition when they are not connected to an active part of the model. So after having said this general information, let's discuss some general aspect of our live demo of today. First, let's look at the model itself. The model consists of a 7-meter sand layer. On top of it, a 6-meter layer of silt and 2-meter of pit. Then we have 2 fill layers, 1 and 2, of 2 meters each. Due to the constraining effect of the soil on either side of a cross-section to the embankment, the displacement normal to the cross-section can be assumed to be 0, so plane strain assumption can be adopted, meaning that we will use a plane strain model. The subsoil, so these 3 layers, is assumed to be founded on a rough and rigid underlying soil rock layer, let's say. So we can constrain the model in X and Y direction at the bottom. The left boundary is a line of symmetry, so only vertical displacement will be allowed, meaning that we will constrain the X direction. And the right-hand boundary is also restrained in the horizontal X direction to simulate the constraining effect of the adjacent soil. We assume the embankment layers are assumed dry through the construction stage, so we won't consider any water level. In the following table, you have a summary of the material property. For the pit, silt, and sand, we will consider a more Coulomb and Drucker-Playa plasticity material model. And for the sand layer, a linear static. For each of these soil layer, we will consider 2 sets of material properties, respectively with undrained and drained condition. And for the undrained condition, for the undrained behavior, we will use the undrained behavior with fluid bulk modulus, as I mentioned previously. Finally, for the construction stage analysis, we will consider the following stages. The first stage, only the 3 soil layers, pit, silt, and sand, will be active. For the 3 soil layers, drain condition will be considered. This is to avoid building up excess port pressure during stress initialization. In the second phase, we had the fill 1, and we switched to unjoined behavior for the 3 soil layers. This corresponds to the short-term behavior. We keep the same strategy for the third construction stage, in which we had fill 2. We keep the unjoined condition for the soil layers, keeping the assumption that the second fill layers is built after fill 1 in a very short time. And finally, last stage, that we call the drainage stage. All the layers are active, and we switch to drain behavior for the soil layers. By doing this, we assume that a long drainage time is provided, long enough to allow all excess pore pressure developed during the construction to dissipate entirely. This corresponds to the long-term behavior of the embankment. So, enough talk, let's move to the modeling part. So first of all, you need to, of course, open your Diana environment, and we start with a new project. So I'm going to call it Embankment Demo. I'm going to move to my folder. As I mentioned during the presentation, we are going to use plane strain model. For the model size, as you may know from previous e-learning session, this is an important input. I'm going to use 1 kilometer. So this is going to define the model, the size of the box in which my model should fit. For the default measure type, we choose exact weight dominant, and I'm going to set a mesh order quadratic for the mid-node location on shape, and then I click OK. Regarding the units, we are going to use meter. For the mass, we choose ton, force in kilonewton, time in second, temperature in Kelvin, and for the angle, I'm going to choose degree. So we are going to first define the geometry, starting with the different layer of our model. I have made, prepared, let's say, an Excel sheet where I've put all the input value of the geometry, so I can just copy paste for making the live demo a little bit faster. So first, I'm going to start with the fill 1 layer. Create fill 1. And I'm going to use the coordinate option. And I'm going to copy my coordinate. This is one way of creating this geometry. Doesn't mean that it's the only one. I zoom out, so this is the fill 1, and I click on create. Keep in mind that you always need to click on the create button until the geometry is created. Now if I move to the geometry tree under shape, you can see that the fill 1 has been created. Then I'm going to create fill 2 using the same method, coordinate. I copy, paste. So fill 2 appear on top of fill 1, then I create the geometry, and you immediately see that the second fill is created. Next, I'm going to create the peak layer. For the peak layer, I'm going to use a rectangle option. I need to define the starting position for the rectangle and basically the diagonal. So the starting point will be 0, 0, so it will be start from here, and the size will be 50 meter on the X direction and minus 2 meter in Z, in Y, sorry. Then I click create, zoom out. We use the same procedure for the tilt layer. The starting point is now 0, -2, 0. The size is 50 and -6 deep. And click create. And finally, the last one, the sand layer. Starting position is 0, -8, 0. Zoom out. Dimension in the X direction is 50 meters and it's 7 meters deep. Then I click create. So I have my fill 1, my fill 2, pit layer, silt, and sand. So basically the different components of the geometry are created. I'm now going to proceed with the property assignment definition in terms of material. So in order to save time, I'm going to import my material property. Otherwise, it will be a lot of typing and we will go through. So for the model section, I need to activate the material and I click on the import button. And I have already made this model before this session. So, and I export it as a data file. And basically you can import material from an existing metadata file. So you see here the different material that I have defined, and that's also the one we are going to use in today's live demo. So I check all and I import. And we will have a look at them, starting with fill 1. So we define some linear property here and the more Coulomb parameter. The same for fill 2. So trust me, and the values specified there are also the one I presented in the table on my slide. Again, here the more Coulomb property. Now let's move to the pit. So as you see, for every sol layer, we have two material, one with drain and one with undrain. So let's check what it means. So for the pit, we choose two aspects to include, the initial stress and the drainage. So this is the important one for today's live demo because that's where you can switch from drain to undrained behavior. So here you have the Young's modulus, pressure ratio, mass density, porosity. Here some more Coulomb and recuperative plasticity parameter. For the initial stress, you have the keynote here value. And for the drainage, here you can choose your drain undrained behavior. So this is a drain material. And let's see the undrained material. So the property here for the linear elasticity, more Coulomb and initial stress are the same. The only difference is here. Oh, it should be undrained, this one. Something went wrong. So we choose the undrained with fluid bulk modulus, and here we specify the value of the bulk modulus here. So this is the difference between the drain and undrained. The same apply to the sand. This is a drain option. No, somehow the import was not what I expected. Here's the undrained behavior. I'm going to also to check my silt. This is a drain behavior. And for the undrained, I have to switch. And here is a fluid bulk modulus value. So this is the important point of today. Do not forget to include this drainage aspect. Then you will be able to switch on the drain or undrained behavior at the material level. I'm going to give some different color to this material so that we can see some differences when we assign the material. So we are going to make our model a little bit more colorful. Okay, so we have defined the geometry. We have defined our material, both with drain condition and undrained condition. So now we are going to assign this property to the different part of our model. So I start with the sand layer. I select the sand layer. For the element class, I choose the regular plane strain. And for the material, I start with the drain one, sand drain. And I click on create. I repeat the same for the silt, regular plane strain, and I choose for the drain condition, create, then the pit, pit drain, create, and then finally fill one, create, and the last one, fill two, regular plane strain, fill two, create. So we have assigned the property in terms of material to the model. Let's now define our boundary condition. So as I mentioned in the short introduction, the bottom will be constrained in X and Y, and the left and right side will be constrained in the X direction. So first I called BCX, which will be part of a support set called BC. I select age. So all this age are constrained in X, create, and then BCY, which will also be part of the same set, and for which I only select the edge type, edge. It will be in Y, create. And now if I look under the geometry tree and the support, I can see my support set, which was the two component BCX and BCY. I don't recall if I mentioned it during my brief presentation about the construction stage analysis. You don't need to define the self-weight load for the geomechanical construction stage. It's by default automatically applied, so you don't have to worry about that. So I'm not going to define any self-weight load. It will be automatically considered in the analysis. So we have the model with material assigned and boundary condition. Let's define some mesh seeding. So I click on the set mesh property, and I'm going to choose target type shape and an element size of 1 meter for the fill 1 and fill 2. I click apply. And for the 3 soil layer, silt, pit, silt, and sand, pit, silt, and sand, I'm also going to use 1 meter. Apply. And I'm going to measure. So you see the different soil layer with different drain property, and we have a complete model. So now let's go to the analysis part, which is also one of the challenge of today. So as I mentioned, we are going to use a geomechanical stage construction. So first I click on add an analysis. that I'm going to rename to Embankment Analysis. And I add the stage construction. I'm going to expand a little bit the window so that you can see it better. Here are the general settings for the geomechanical. I'm going to start with the output, and I'm going to specify some output directly. I'm going to ask for the displacement. What else I'm going to ask for the strain, plastic strain. Volumetric. Don't miss this as well. What else I'm going to ask? Also the stress. The effective stress. Total stress. And the pressure. This result pressure will be only available for the phase with undrained condition. So that's it for the results. Next to that, I'm going to give some information about the iteration. For the maximum number of iteration, I go for 5. Convergence tolerance, 1 per mil. Maximum number of iteration 10. For the method, I'm going to use constant stiffness, and I want only the force norm to be satisfied. So these are for the general consideration that will be used for the different stage of the analysis. Now we are going to build the different phase or stage. So I right-click on the geomechanical stage construction, and I add a stage. So my first stage is the one I called initial stage. And I'm going to look at the active part of the model. So in this initial phase, as I said, there's no water present. I'm going to clear displacement. I'm going to use a number of increment of 1. And in terms of active set, the fill 1 won't be there, the fill 2 won't be there. Only the pit, silt, and sand will be there with drained condition. And I don't specify any load, but the self-weight load will be automatically applied. So this is the first phase. I'm going to duplicate this phase and rename it to add fill 1. So I rename it, expand it, and I look at the active part. So still no water present for this one, number of increment stay 1. And here the pit, drain, and undrain are going to change. I set pit to undrain, silt to undrain, and the same for sand, undrain. And I activate the first fill layer. We repeat the same procedure. We duplicate this fill at fill 1 stage. It automatically rename it to add fill 2. And we go to the active part of the model. In the meantime, you can see that at the mesh level, you see the active mesh set. So no water present, this is keep constant. 1, we add the fill 2. The pit, silt, and sand keep their undrained condition. And in terms of load, the self-weight will be automatically applied. So last phase, I'm going to duplicate this one, and I'm going to call it the drainage phase. For the active part of the model, everything is active, so just like in the previous phase. But here we are going to switch back to drain condition, so the pit gets a pit drain condition, the same for silt, and finally the same for sand. So we have our 4 phase. You can see the 4 phase here with the different option, and for individual phase you can check the status and the active mesh part. So initial phase with soil layer in undrained condition, then we start adding the fill 1, and we have initial phase with drain condition, then we add the fill 1 and the soil layer are undrained. We add the second layer again with undrained condition, and finally we drain the model by switching back to drain condition for the soil layer. So our analysis setup is done. We can run the analysis and finally look at the results. So I have already run the analysis to save some time, although this analysis is not taking so much time, but to prevent any problem, I already run it. So just a last check to make sure that the phase are properly defined. So first we start with initial phase with drain condition, then we add the fill 1 under undrained condition, the fill 2 undrained condition, and then the drainage phase where we set everything to drain. So first we can look at the effective stress. So I zoom out. This is the initial phase, so only the sand, silt, and pit layers, so the soil layers. And you can see that we have a nice distribution. And if I move through the phase, you will see the evolution of the effective stresses. So here we switch to undrained condition, and we add the first fill layer, then the second fill layer, and finally redrain the model. Next, we can look at the plastic strain. I'm going back to the initial phase, and if I go under total strain, from the second phase, I should see some plastic strain. So there's no plastic strain in the first phase. It's all elastic. And I look at the volumetric one. You can see after building the fill 1, some plastic strain developing, then fill 2, and then the drainage. We can have a look at the excess pore pressure, which is basically the pore water pressure generated by the loading, by loading the soil. So this result is only available for the stage 2 and stage 3, where we have undrained condition. So I'm going to add fill 1, pore pressure. So you see the distribution after adding the fill 1 layer, and then the excess pore pressure after adding the second fill layer. Last output we can look, and which is quite interesting, it's displacement. Again, I switch back to fill 1, and I'm going to present the displacement as a vector plot. And from this vector plot, you see that we have added fill 1, and then I go to the next one, fill 2. You can recognize that the failure mechanism is rotational. For the one who follow on a regular basis e-learning session, I invite you to refer to the presentation I gave about slope stability, and where I presented the possible failure mode for slope. And one of them was the rotational one that you can identify here. So this is under the unjoined condition. Now, when we look at the long-term behavior after drainage, you see that the displacement change, and basically the embankment doesn't fail. As you can see from the message box, the analysis run to the end, so we are not talking about failure in this case. The model is stable. But the drainage, basically, of the drainage of the subsoil prevents the development of excess pressure and stabilizes the embankment, basically. Thank you very much. Have a good day. Bye.